is in two pictures of time evolution. We have the Schrodinger picture and the Heisenberg picture, right? In the Schrodinger picture, state gets, right? Gets evolve with time. I think I'll just write Schrodinger picture. We had two pictures already. The Schrodinger picture of time evolution, in which the states evolve with time, and let's say the observables are frozen. Okay, the observables frozen. And how does the state evolve? We know that alpha t0 at time t. Okay, again this notation means that the state of the system was get alpha at time t0. That's in notation artham. Okay, this is equal to, we wrote that you can write as u of t comma let's say t comma t0. I think this is how we wrote, acting on alpha comma t0 t0, right? I think this is how we wrote it. Or e state simple alpha comma t0, right? And we found that this this unitary operator had some form. In general, it has the form, if the Hamiltonian is simple, and so it has the form e raised to minus IH t minus t0 divided by h cross. This is the Schrodinger picture. Right? In the Heisenberg picture also we can do the same thing. In other words, the states evolve and the evolution is governed by, okay, I'll just give the features here so that we can compare, and the evolution is governed by the Hamiltonian, correct? Full Hamiltonian, okay, the full Hamiltonian. Okay, and in the Heisenberg picture, okay, in the Heisenberg picture, what we had was the states are frozen. The states are considered to be frozen in time, okay, and the operators evolve, okay, and they evolve according to what equation? Again, the evolution is governed by this unitary operator, right? So what was the condition? We know that a of t is equal to, right? This is in the Heisenberg picture, and the Schrodinger picture but let's, I think I should write subscript s here to avoid confusion. H of t was equal to, or t plus dt, or I don't know how we wrote it. I think we can write as h of t. Okay, time t, this is equal to, did we write u dagger first? Yeah, it has to be u dagger ah at time 0, okay, which is also equal to as at time, at all times. Okay, this is how the operators evolved. Okay, so this evolve state evolve operator change assume states change operator equations evolve assume. In any case, the evolution of the expectation values, right, the evolution of expectation values are exactly the same. Right? That's why we say that these are equivalent. Right? Now, there's another picture intermediate between these two. Actually, you can construct any number of pictures. Right? But there is one particular picture that's useful, which is called as an interaction picture, or interaction picture or intermediate picture. Right? In this case, we'll consider that the Hamiltonian has two parts. Right? The Hamiltonian has two parts, and both states and operators evolve. All right. So in the interaction picture that we are going to see, both states and the operators evolve with time. Okay. So if the we'll see that the Hamiltonian can be nicely written into two parts. One part of the Hamiltonian will govern the evolution of the states, and the other part of the Hamiltonian will govern the evolution of operators. All right. This is what we are going to see. All right. I hope this is clear. Okay. So the interaction picture, we use this in terms of, in the case where there's a small perturbation, a time dependent perturbation, etc. Right? We'll be discussing this in detail in the third semester. Right? You'll have one whole section on this. So we'll just write the relevant details here. The interaction picture is useful in situations. The interaction picture is useful in situations where the Hamiltonian the Hamiltonian has two parts, all right, or Hamiltonian can be written as sum of two parts, can be, let's say, split into two parts. Okay, and there is a specific way to split this, all right. We'll write it, it's convenient, okay, the interaction picture is useful if you can write the Hamiltonian as an H0 plus, let's say, V, which generally also can depend on time, all right. H0 plus V. Okay, so split this H0 is supposed to be a non-Hamiltonian, all right. Perturbation we completely solve it, and eigenvalues and eigenvectors are Hamiltonian part and H0. All right. For example, you may have the simple harmonic oscillator Hamiltonian plus some other part. All right. Simple harmonic Hamiltonian namukku thannu, and a simple harmonic oscillator and Hamiltonian plus some extra term then we can use this. All right, because we already know the complete eigenvalues and eigenvectors for H0. All right. So what is H0? One thing is H0 does not contain time. The time dependence is fully given to this V part. Okay, does not contain time explicitly. All right. This is the situation in which the interaction picture is more useful. That's all right. All right, and also the eigen values, right, H0 Hamiltonian is considered to be completely solved. All right, so eigenvalues, this means that the eigenvalues and eigenvectors of H0 are known. Okay. This means that we know this relation, all right. For example, H0 n is equal to En ket n, all right. The assumption is that the H0 part is completely known, all right. These are things that we have worked out. For example, it could be a simple harmonic oscillator Hamiltonian that we just did, all right, plus an extra term, all right. Now, we know everything about H0, all right. So, the H0 is the completely solved part, okay, and it is certainly Hermitian. Okay, both V and H are Hermitian, all right, because the total Hamiltonian has to be Hermitian, and it is certainly Hermitian. Both these have to be Hermitian, all right. H has to be Hermitian, H0 is Hermitian, so V is also Hermitian. Okay. Now, this H0 is a Hermitian operator. We know that Hermitian operators generate unitary transformations. Am I right? Do we know that? We know that if you have a Hermitian operator, you can directly write a corresponding unitary transformation. Okay? If you are given a Hermitian operator, you can write a unitary transformation, right? You just do this. If you are given a Hermitian operator A, then e raised to IA, let's say there is some parameter, real parameter A, then this is a unitary operator. Why is it a unitary operator? All right, so we can say that any operator, Hermitian operator, generates a unitary transformation. Why is this a unitary operator? Because if you take U dagger, what is U dagger? Here, this is U. U dagger is just e raised to minus I epsilon A dagger, but A dagger is equal to A if it's Hermitian. So this is I. Okay, so you see that U dagger U is equal to I. So if you have a Hermitian operator, you can directly write a corresponding unitary transformation of this form. It works. All right. So we know that H0 is a unitary transformation, and clearly, we know that H0 is a Hermitian operator, and clearly it generates its own unitary transformation. All right, that's our premise. All right. So we can say that so H0 generates some sort of a unitary transformation. All right, we don't know what, but we'll use it. Generates some. It makes some unitary transformation. It generates some unitary transformation. Okay. So we look at the following unitary transformation, right? Let us look at the following unitary transformation. Okay, let's look at the following unitary transformation. and we'll write it like this. We can, okay, I'll write it like this. Okay, I'll call alpha t0 t. Okay, alpha t0 t. This means that we are talking about some time here, and this the initial at time t0 the state was alpha, etc. Right. So we are looking at this particular unitary transformation e raised to I h0 t divided by h cross. Okay, I'll call this as alpha, ket alpha with the subscript I, because this I will call the states in the interaction picture. Okay, this I stands for interaction picture. All right, and then you can act it on the state in the Schrodinger picture S. Okay, so this is actually a definition. I define the interaction picture ket, okay, the interaction picture ket in terms of this unitary transformation on the interaction picture, in the Schrodinger picture ket. Okay, അപ്പോൾ നിങ്ങൾ ഒരു കാര്യം നോക്കുകയാണെങ്കിൽ നമുക്ക് എക്സ്ട്രാ ടേം വി എന്നുള്ള എക്സ്ട്രാ ടേം ഇല്ലായിരുന്നെങ്കിൽ, ഓക്കെ, വി എന്നുള്ള എക്സ്ട്രാ ടേം ഇല്ലായിരുന്നെങ്കിൽ ദിസ് ഈസ് എക്സാക്ട്ലി ദ റിലേഷൻ ബിറ്റ്വീൻ, ഓക്കെ, സോ വെൽ സേ വിത്തൗട്ട് ഓർ വിത്ത് വി ഈസ് ഈക്വൽ ടു 0. ഓക്കെ, ദിസ് ഈസ് എക്സാക്ട്ലി the relation between states in the Heisenberg and Schrodinger pictures. Is that correct? Okay, അതായത് t എന്നുള്ള ടൈമിലുള്ള ഷ്രോഡിംഗർ പിക്ചറിൻ്റെ സ്റ്റേറ്റ് എടുക്കുകയാണ്. ഓൾറൈറ്റ്, ആൻഡ് ദെൻ ഇഫ് ദർ ഇസ് നോ വി, ഓൾറൈറ്റ്, വി എന്നുള്ള ഇതില്ലെങ്കിൽ വി ആർ മേക്കിംഗ് ഇറ്റ് ടു അനദർ സ്റ്റേറ്റ്. ഓൾറൈറ്റ്, ആൻഡ് വി ആർ മേക്കിംഗ് എ ട്രാൻസ്ഫർമേഷൻ. ദിസ് ഇസ് ആക്ച്വലി ട്രാൻസ്ഫർമേഷൻ ബാക്ക്വേർഡ്സ് ഇൻ ടൈം. റൈറ്റ്, നമ്മൾ യു എന്ന് പറയുന്നത് ഇറ്റ് ടേക്സ് ദ സ്റ്റേറ്റ് ഫോർവേഡ്സ് ഇൻ ടൈം, ഇസ് ടു മൈനസ് ഐ എച്ച് 0 ടി ബൈ എച്ച് ക്രോസ്. This takes the state forward in time. This actually is taking the state backward in time, because the state, Schrodinger state, has evolved in time. The Schrodinger state എന്ന് പറയുന്നത് ടൈമിൽ ഇവോൾവ് ചെയ്തിട്ടുണ്ട്. ടി എന്നുള്ള സമയത്ത് ഇപ്പോൾ ഇറ്റ്സ് ഇൻ സം സ്റ്റേറ്റ് ആൽഫ കൊമ ടി 0 ടി. Okay, in the Schrodinger picture, what we do is that we are taking it back in time, right, using this unitary operator. Okay, so this is a ket which does not depend on time, when v is equal to 0. Right, നമ്മുടെ v എന്നുള്ള എക്സ്ട്രാ ഭാഗം ഇല്ലെങ്കിൽ, okay, if v എന്നുള്ള എക്സ്ട്രാ ഭാഗം ഇല്ലെങ്കിൽ, this is just the initial state. Alright, this is just the state at t equal to 0. This is just the state at t equal to 0. അതായത് v എന്നുള്ള ഇനീഷ്യൽ ഭാഗം ഇല്ലെങ്കിൽ, this is just your Heisenberg picture state. നിങ്ങൾക്ക് ഓർമ്മയുണ്ടെങ്കിൽ, I don't know how we wrote it at that time. Alpha, did we write it like this? Yeah, നമ്മളിവിടെ h ഇടാമായിരുന്നു. If there is no v term, we could simply write an h here, and this would be the state in the Heisenberg picture. Alright, but we know that the full time evolution is generated by the full Hamiltonian, not just this part. Alright, so even though we have taken it back in time, there is still some time dependence here because of this v part. Alright, v part is time dependence. That's the reason why I don't write an h here, but I write an I. Is that clear? Is this part fine? Is this definition okay with you? Is anyone following? Is there any question there? Is anyone there still? Yeah, is this part clear? Is it fine?
Yes, sir.
Alright, so the Heisenberg picture ഇതും ഉള്ള പോലെ തന്നെയാണ്. ഹൈസൻബർഗ് പിക്ചറിലെ സ്റ്റേറ്റ്സും സ്ട്രോഡിംഗർ പിക്ചറിലെ സ്റ്റേറ്റും തമ്മിലുള്ള റിലേഷൻ തന്നെയാണിത്. ഓക്കെ, എക്സെപ്റ്റ് ഹൈസൻബർഗ് പിക്ചറിൽ ഇവിടെ ഫുൾ ഹാമിൽട്ടോണിയൻ ആവുമായിരുന്നു, ഇവിടെ ഹാമിൽട്ടോണിൻ്റെ ഒരു ഭാഗം മാത്രം നമ്മൾ എടുത്തിട്ടുണ്ട്. ദാറ്റ്സ് ഓൾ. Okay, so this is kind of a definition of the interaction picture state. Okay, this we call kets in the interaction picture. Right, this we call as the kets in the interaction picture. Okay, so now let's check the time evolution. Let us check the time evolution. Let's check the time evolution of the state alpha t0 t in the interaction picture. Okay, ഇതിൻ്റെ ടൈം എവല്യൂഷൻ നമ്മൾ ചെക്ക് ചെയ്യുകയാണ്. ഇതിൻ്റെ ടൈം എവല്യൂഷൻ ചെക്ക് ചെയ്യുമ്പോൾ നമ്മൾ വാട്ട് ഡു യു എക്സ്പെക്ട്? റൈറ്റ്, ഇവിടെ നമ്മൾ ചെയ്തിരിക്കുന്ന ആക്ച്വലി ഫുൾ ഹാമിൽട്ടോണിയൻ ആണ് ടൈം എവല്യൂഷന് കാരണമാകുന്നത്. അതിൽ h0 ഭാഗത്തിന് ടൈം എവല്യൂഷൻ വി ആർ കൈൻഡ് ഓഫ് ക്യാൻസലിംഗ്. റൈറ്റ്, വി ആർ ടേക്കിംഗ് ഇറ്റ് ബാക്ക് ഇൻ ടൈം വിത്ത് റെസ്പെക്ട് ടു h0, സംതിങ് ലൈക്ക് ദാറ്റ്. റൈറ്റ്, സോ വാട്ട് വി എക്സ്പെക്ട് ഇസ് ദാറ്റ് ദ ടൈം എവല്യൂഷൻ ഓഫ് this particular state, okay, the time evolution of this particular state will be governed by the second part of the Hamiltonian. In the time evolution, it will be governed by the second part of the Hamiltonian. That's what we expect. All right. Is that clear? Because we take the state at any time, you take it back in time, all right, using the operator h0. But still there is some residual time dependence on this because of the operator v. Because Hamiltonian, the full Hamiltonian generates time evolution, not part of it. All right. So let's see if this intuition is correct. Okay. I hope this intuition is fine. Let's see if this is correct. All right. So let's check the time evolution of this ket. So what we do is you take the time derivative d by dt of alpha comma t0 t at I. Okay, so not at I in the interaction picture. This is equal to, you just take the time derivative on the other side also, right? This is equal to e raised to I h0 t divided by h cross in the Schrodinger picture. Okay. All right. Now what do we do now? So we assume that this h0 has no explicit time dependence, etc. That's the basic starting assumption, all right? h0 does not contain time explicitly. So we can just use the product rule here. Okay, you can use the product rule. So this becomes, so if you use the product rule, this becomes I h0 hat divided by h cross. That's the time derivative. All right, this is of the form e raised to iax or something. So this is a e raised to iax, right? So that this part you're taking time derivative with respect to time, so you get out this part I h0 divided by h cross. Is that fine? What do we have here? It's e raised to I h0 t divided by h cross. Okay, first term derivative adelle. Schrodinger part. This is only the first part. Okay, you also you have to use the product rule, right? So there's also one more part to this. This is e raised to I h0 t divided by h cross, and then alpha, we'll write it as d by dt. Maybe I should have written it as a partial derivative, but I'm not being very, you can check that, all right? But it's all right. I think there's only t here, t0 we assume that is fixed, so it's fine, I think. Maybe it's more accurate to write partial derivative, but for now let me write it like this. So this is d by dt of alpha t0 t in the Schrodinger picture. Okay, all right. Now we see that it's maybe it's convenient to write IH cross d by dt, all right? So you multiply by IH cross on both sides, so IH cross d by dt. I think I should go to the next page. Okay, so you just do, let me copy this. Right, I think I'm out of page here. Maybe I'll just write it once more here in a small way, right? So I'll write it here. What we did right now is I'll just multiply this previous equation with IH cross. So IH cross d by dt of alpha t0 t, what we called it as the interaction picture, all right? So this is equal to IH0 divided by h cross, sorry, I multiply it with IH cross, all right? Minus, we have IH0 by h cross. If I multiply it by IH cross, this h cross and h cross will cancel. This I will multiply this I and give you minus 1. So that is minus h0 hat. Is that correct? And e raised to minus IH0 hat t divided by h cross. Okay. And you have got this alpha t0 t in the Schrodinger picture right there, all right, plus I'll write this as e raised to IH0 t by h cross, okay, this term, it's this term, and then I'll write the rest as IH cross d by dt of alpha comma t0 t in the Schrodinger picture, all right? Is this okay? I hope this. So what do we do now? We already know this, all right? We already know how the state evolves in the Schrodinger picture, right? We already know okay, we already know that IH cross d by dt of alpha t0 t is equal to, what is it? This is equal to is the Schrodinger equation, right? We already have done this. What's the result? This is equal to, the Schrodinger picture is equal to, give me the answer. It's H. Okay, we time evolution adding charge the equation, you can check that. So this is the basic Schrodinger equation. This is the basic Schrodinger equation. Except that it's a full Hamiltonian. Alright, it's the full Hamiltonian that governs the time evolution of the Schrodinger cat. Okay? In this case, I can write it as that's equal to H0 plus V. Okay, I'm not writing the argument in here. H0 plus V and then alpha T0 T. Okay, this is the Schrodinger picture, time evolution of a state. This we have already seen. So from here we see that, so I h cos d by dt of alpha T0 T in the interaction picture is equal to, first term I just write it like that, minus I h0 T by h cross alpha T0 T s plus e raised to I h0 T by h cross. Alright, this IH cos d by dt, I will now write it as H0 plus V. Okay, I am just using this equation. Alright, I am just using this equation. This H0 plus V alpha T0 T, the Schrodinger picture. Is that fine? Yeah? Alright, now what do we do? Actually, we have a cancellation here. Okay, so I think I'll do the cancellation first. So this I can write as minus h0 e raised to minus h0 hat t by h cross alpha t0 t s plus, this is, see this, if you look at this term, right, there's a h0 sitting here, there's an h0 hat sitting here, this also an h0 hat, but they commute, all right, they commute because it's the same operator, right? So it doesn't cost you anything to take it to this side. Okay, fine. So this I write as h0 e raised to I h0 t by h cross. Okay, and then you have got this alpha t0 t plus there's also this term e raised to I h0 t divided by h cross. Okay, and then there is this v hat. I'll write it here, plus this term is there, e raised to I h0 t by h cross, and then you have got this v hat alpha t0 t Schrodinger. Okay, so these are the same, right? Two terms same alle with a minus sign. So these two terms will cancel. Is that fine? Okay. All right. Is anybody there? Is that fine? Okay. ഏതെങ്കിലും സ്റ്റെപ്പിൽ സംശയം ഉണ്ടോ ഇതുവരെ ചെയ്തതിൽ? ഓക്കെ അല്ലേ? നിങ്ങൾ ഇടയ്ക്ക് ആൻസർ ചെയ്യണം, അല്ലെങ്കിൽ ദ കണക്ഷൻ ഈസ് എ ബിറ്റ് ബാഡ് ഹിയർ. സോ ഇഫ് ഐ ലൂസ് ദ കണക്ഷൻ ഐ വുഡൻ നോ. റൈറ്റ്, നിങ്ങൾ ഇടയ്ക്ക് ചോദ്യം ചോദിക്കുന്നത് അതുകൊണ്ടും കൂടെയാണ്. If you give me a reply, I know that we are still connected, all right? Otherwise, there's a problem. Okay? So this term is 0. So now we have a simple thing, e raised to I h0 t divided by h cross, and I have a v hat here, right? Now I can do something. I can introduce an identity or a unit operator in here. I'll write it in this form, e raised to minus I h0 t divided by h cross, and then e raised to I h0 t divided by h cross. Okay, what is this? This is equal to 1 in the operator form, correct? Basically I have done a u dagger. Okay, I have given a u dagger, but in terms of the h0 part. Okay, and then alpha t0 t. Why did I do this? Because I have this alpha t0 t here. Then this is in the Schrodinger picture. If I do this, I can get again this alpha t0 t I, right? Because by definition this was equal to what? By definition, this is the definition that we started with. Alpha t0 t I is equal to e raised to I h0 t h cross, correct? Is that fine? So what you have here is e raised to I h0 t divided by h cross. Okay, I'll just make it short, and I'll write this as vi hat. Okay, I'll write it as vi hat alpha t0 t in the interaction picture. Correct? Okay, now why did I call this as Vi? This again looks like an operator transformation, right? The operator transformation pole thanne undu. Okay, so this looks like the operator transformation of a Heisenberg operator, right? This looks like the operator transformation Heisenberg operator. Heisenberg operator inde time evolution ingeneയാണ് കാണിക്കുന്നത്. Correct? With e raised to h0 t and with u dagger and u on both sides. Alright, so that's the reason why I call this as Vi. And the definition of Vi being this is equal to, this is related to the Schrodinger picture V in this manner, I h0 t by h cross. Okay, in നമ്മുടെ full Hamiltonian h0 ആയിരുന്നെങ്കിൽ, okay, h0 നമ്മുടെ full Hamiltonian ആയിരുന്നെങ്കിൽ, this is just the Heisenberg picture operator. This is just the Heisenberg picture operator. But our full Hamiltonian is not h0. So this particular combination we call it as a interaction picture operator. All right, this we call it as the interaction picture operator. V e raised to minus I h0 t divided by h cross. Okay, if you want you can put an s there, but let's not make it too complicated. All right, is this okay? Now we'll use this as a guide for we see that the interaction picture state evolves, or the evolution is governed by the potential energy part of your Hamiltonian. All right, and do we have our operator evolution yet? Okay, the operator itself, the evolution of operator itself is governed by this h0. All right, so I'll just write it like this. So we can take this as a guide. Okay, we can take this as the guiding equation and say that generally operators are related like this. Okay, you could also start with this as the definition. All right, so this gives us a way to define the operator in interaction picture. So this is how we define the operator in our interaction picture. We'll define it like this. It is e raised to I h0 t. I think I should write it as a definition. This Vi എന്നുള്ളതിന് മാത്രമല്ല, I'll take this as the definition of all interaction picture operators. All right, I'll take this as the definition for all interaction picture operators. All right, this is e raised to I h0 t, and then we have this V cap e raised to minus I h0. Oh, sorry, this is a. Okay, I'll be specific here. This is the operator in the Schrodinger picture, and this is the operator in the interaction picture. Okay, this is the operator in the interaction picture. Is that all right? Okay, so in Heisenberg picture, let's just compare this with the Heisenberg picture. We had, what did we have? I'll just write it as alpha h is equal to e raised to I h t divided by h cross, acting on alpha comma t0 equal to 0. Okay, I think I was not very specific before. This in the Schrodinger picture. All right, so our expression for the interaction picture state is exactly the same. Okay, it's exactly the same, except that, okay, the Hamiltonian picture interaction picture state in the definition, it's exactly the same, except that in the Heisenberg picture what you have here is the full Hamiltonian. All right, in the interaction picture what you have here is only part of the Hamiltonian, only the known part of the Hamiltonian. All right, and in the Heisenberg picture we also had ah is equal to e raised to I h t by h cross. A is the Schrodinger picture operator, e raised to minus I h t divided by h cross. Okay, is this clear? So the basic difference between Heisenberg and interaction picture is that in the Heisenberg picture the full Hamiltonian. The full Hamiltonian appears, and in interaction picture only H0 appears. Okay, in this relation, right? The other part also appears somewhere else, but in this relations only H0 appear. All right. അതായത് ഇൻട്രാക്ഷൻ പിക്ചർ നമ്മളിവിടെ പറഞ്ഞു തന്നത് ഇൻട്രാക്ഷൻ പിക്ചറിലാണെങ്കിൽ സ്റ്റേറ്റ്സും ഇവോൾവ് ചെയ്യും, ഓപ്പറേറ്റേഴ്സ് ഇവോൾവ് ചെയ്യും. റൈറ്റ്. സോ സ്റ്റേറ്റ്സ് in Schrodinger picture only states evolve, in Heisenberg picture only operators evolve. In interaction picture both states and operators evolve. The operator evolution is governed by H0, okay, the H0 part of the Hamiltonian, and the state evolution is governed by the rest of the Hamiltonian, okay, the V part of the Hamiltonian. All right, that's the idea. Now let's look at the interaction picture equation of motion. Interaction picture, let's say time evolution. Let's check the time evolution of the operator. Okay, so we can do dAi divided by dt. Okay, what was ai? Ai is defined as e raised to IH0t as. Okay, this is the definition for ai. I think I should write it here itself. Okay, I'll just write it again. So what we have here is ai hat is equal to e raised to IH0t a hat s also H cos. Right. So we can find dAi divided by dt. You have to use the product rule, so this becomes IH0 divided by t e raised to IH0 t by H cos. Okay, and you have got this as, right, and the other part is raised to minus IH0 t divided by H cos. You are using the product rule, right? So you also should actually use it for as, but we assume that as has no explicit dependence on time, and in general the Schrodinger picture operators are frozen in time, so this part doesn't change. So this becomes e raised to IH0. Yes,
IH0 by H cross.
Correct, good, it's H cross. Okay, thank you. So it is e raised to IH0 t as, and then what do we have here? Minus IH0 by H cross, correct? Is that correct, or did I make a mistake? This minus there. Is that correct? All right, so this I can write it as, what is this? This is our definition for ai, correct? This is our definition for ai. So that is IH0 divided by H cos ai, okay, plus ai hat. Okay, this is again ai, right? This is again ai. This is the definition for ai. We are just using it here, and then you have got ai minus IH0 hat divided by H cos. Okay, so you can take this 1 by IH cos outside. Right, I have take this 1 by IH cos outside. 1 by IH cos outside, I am putting an extra minus, and I am taking this I to the denominator. Basically, multiplying and dividing by I. Okay, so you'll get a minus sign here. So that minus will cancel with this minus, and it will become plus. So I take this 1 by IH cos outside. This becomes ai hat H0 minus, okay, term H0 ai. Is that fine? Okay, I hope that minus sign is fine. All right, so that I can write as 1 by IH cos, the commutator of ai with H0. Okay, so this is dAi divided by dt. Again, this looks exactly like the time evolution of the operator in your Heisenberg picture, correct? Except that Heisenberg picture we have a full Hamiltonian until here we only have the interaction part of the Hamiltonian. Okay, all right, and complete the box. Okay, is this all right?
Okay, sir.
Now I think ഇത്രയും കാര്യങ്ങൾ മതി. ഓൾറൈറ്റ്, നമ്മുടെ ഇൻറ്ററാക്ഷൻ പിക്ചറായിട്ട് ബന്ധപ്പെട്ട് ഇത്രയും കാര്യങ്ങൾ മതി. ഇതിൻ്റെ ബാക്കി ഡീറ്റെയിൽസ് നമ്മൾ അടുത്ത സെമിസ്റ്ററിൽ ചെയ്യുന്നുണ്ടാവും. നമ്മൾ പെർട്ടർബേഷൻ തിയറി ഉപയോഗിച്ച് ഇത്തരം പ്രോബ്ലംസ് സോൾവ് ചെയ്യണം. വി എന്നുള്ള വി എന്നുള്ള പാർട്ട് ടൈം ഡിപ്പെൻഡൻ്റ് ആണെങ്കിൽ നമ്മൾ ഈ പിക്ചർ ഉപയോഗിച്ച് നമ്മൾ സോൾവ് ചെയ്യും. ഓക്കെ, സോൾവ് ചെയ്യുമ്പോൾ നമ്മൾ ആദ്യം ചെയ്യേണ്ടത് ശരിക്കും ഇതിന് കറസ്പോണ്ട് ചെയ്യുന്ന യൂണിറ്ററി ഓപ്പറേറ്റർ കണ്ടുപിടിക്കുക എന്നുള്ളതാണ്. യൂണിറ്ററി ഓപ്പറേറ്ററിൻ്റെ ഇക്വേഷൻ നമ്മൾ എഴുതും. അതിൻ്റെ ഒരു ജനറൽ സൊല്യൂഷൻ എന്നുള്ള രീതിയിൽ ഒരു പെർട്ടർബേഷൻ സീരീസ് നമ്മൾ എഴുതും. റൈറ്റ്, ഇറ്റ്സ് കോൾഡ് ദ ഡൈസൺ സീരീസ് എറ്റ്സെട്ര. റൈറ്റ്, ബട്ട് you are only asked some features of this interaction picture, so this is enough for the time being. All right, we are not worried about what kind of V we have, etc. All right, so for the time being this is enough. നമ്മൾ ഹൈസൻബർഗ് പിക്ചർ ഉണ്ട്, ഷ്രോഡിംഗർ പിക്ചർ ഉണ്ട്, അതേ രീതിയിൽ ഇൻട്രാക്ഷൻ പിക്ചറും ഡിസ്കസ് ചെയ്തു. ഇത്രയും ഡീറ്റെയിൽസ് മതി. റൈറ്റ്, സോ വിൽ ജസ്റ്റ് സോൾവ് ഇറ്റ്, വിൽ ജസ്റ്റ് കൺക്ലൂഡ് ബൈ summarizing this thing. All right, so what we have seen is that the interaction picture or it's also called the Dirac picture, okay, is intermediate between the Schrödinger and Heisenberg pictures. Okay, so we can draw a table to compare. Okay, we can draw a table to compare. So we'll draw the table like this. We have, on the one hand, we have got Heisenberg picture, okay, and we'll put the Dirac picture in between. The Dirac picture is the interaction picture. Okay, we'll call it the Dirac picture because this is called Heisenberg, the other one is called Schrödinger, so we'll call this Dirac. It's nice, all right. So Dirac gets some credit. This is the Schrödinger picture, all right. And I think this is fine. So first we discuss the evolution of state gets. All right. So state gets, what happens to state gets in Heisenberg picture? What happens to state gets in Heisenberg picture? There's no change. Is that correct? Yeah. In Dirac picture, the evolution, it changes, and the evolution is determined by VI. Okay, the evolution is determined by VI, and we know what VI is here. You can check back, all right. And in the Schrödinger picture, the state gets, evolution is determined by H. Okay, and then you can talk about observables or operators. I think observables is fine. All right. In Heisenberg picture, the evolution is determined by the full Hamiltonian. Okay. In the Dirac picture, the evolution is determined by H0. Okay. In this case, the operators do not change. In the Schrödinger picture, the operators do not change. Should I draw lines here for the table? No, I think this is fine. Okay, I think this is fine. So this is the summary of the three pictures. Okay, we have got Heisenberg picture, Dirac picture, and Schrödinger picture, and the Dirac picture or the interaction picture is intermediate between Heisenberg and Schrödinger pictures. All right.